great pleasure to speak in this conference again. So the goal of my talk is to use the Conley theory to obtain dynamical applications. And for me, as someone working in symplectic topology, I guess probably I speak for lots of people working in symplectic topology. I think it's fair to say that we like Morse theory, right? In some sense or not. And Conley theory is the possibility of using Morse theoretical arguments to study flows which are not gradient-like. So I think it's interesting that we have this possibility. And unfortunately, the kind of flows that we study are volume-preserving, conservative flows, which means that by Poincare recurrence, the flow is certainly not Morse theoretical. It's not a gradient flow, it's a recurrent flow. So, but then with Conley theory, you can again open the possibility of studying like this recurrent flow by Morse theoretical methods. Okay, so let me briefly recall a bit of Conley theory. So for the first 15 minutes or so, I will study a flow, I'll consider a flow on a manifold, a smooth flow on a smooth manifold. And the first ingredient that you need to get a Morse-like theory is to have the analog of the Morse index well defined. So let me tell you a bit about that. So first, a bit of notation. So if you have a subset of our manifold equipped with the flow, I will denote by Sn the maximal invariant set containing n. So set of points for each set of points of n, for each all the trajectory to that point in the past and the future is containing n. All right. An isolating neighborhood is a compact subset n such that the maximal invariant set is contained in the interior of n. So that's the notion of isolation. And then, so in this case, this invariant set is said to be isolated. So an invariant set S is isolated if S equals to Sn for some isolating neighborhood. Okay? So what's a typical example? Typical example is an isolated critical point, say a non-degenerate critical point of a gradient flow. All right. I will say that the flow goes through n if Sn is the empty set. So it could be empty. Okay. A pair n1, n2 of compact subsets of n is a Conley pair if the following holds. One, these compact subsets are positively invariant with respect to n. So if I have a point in Nj, and some piece of the future of x is contained in N, then that piece is also contained in Nj, so positive invariance. 2, the maximal invariant subset of N is contained in the interior of N1 minus N2. And 3, if I have a point in N1 which is going to leave N, then it's going to leave through N2. So there exists T such that this is containing N, but the final point is a point in N2. Okay? I do not require, as is usual, that N2 is contained in N1. Right? Yes? Sorry? So if I have a point in N1 or N2, and if up to time t stays in N, then actually up to time t stays in N1 or N2. Right? So it's positive invariance. If I start in N1, let's say, and I stay up to some time t in N, that means I'm still in N1. So what is the typical example? Well, the typical example of such an object is what you get looking at the neighborhood of a non-degenerate critical point. Let me, before drawing the picture, make a definition. So if I have S isolated invariant set, the homotopic Conley index is, let me denote it by H of S, is the homotopy type of N1 modulo N2, where N1 and 2 is a Conley pair in some isolating neighborhood. So this space is the homotopy type of a pointed space obtained by consider N1 union N2, collapsing N2 to a point, and the marked point is N2. So the simplest example is non-degenerate critical point. Let's say you have a critical point of index mu, non-degenerate, right? So you have stable and unstable manifolds. So here's an isolating neighborhood. So you can take something like that to be N1. This is N1. And then N2, something looking like that. So here's N2. And then the homotopy type here is the homotopy type of a pointed sphere of dimension mu. Okay? Right? I mean, basically, is the unstable, a piece of the unstable disk modulo boundary. Okay. So this means that this is a proper generalization of the Morse index, but for an invariant set, isolated one. All right. Next ingredient I need is something that is common in dynamics, but maybe in the symplectic community is not so common. Well, it's not such a widespread notion. Is the notion of chain recurrence. Okay. So I give you two positive numbers, epsilon t. An epsilon t chain is a pair of sequences the pair of sequences. Let's say epsilon t chain from P to Q is a pair of sequences starting at the point P, ending at the point Q, plus a bunch of numbers, such that what? Such that all these numbers are at least equal to t, and the distance between phi ti xi minus 1 to xi is less or equal than epsilon. So I fix a metric compatible with the topology of the manifold. Okay, so the chain recurrent set. So this means what? This means you're allowed to go from a point to another. You can flow, but you have to flow for some time t, and you can make a small error of size epsilon. So the chain recurrent set, the set of points P, such that for all epsilon t, there exists epsilon t chain from P to P. So it's a closed invariant set. It contains all the recurrent points. So for instance, if you have a Hebb flow in a compact manifold, by Poincare recurrence is going to be the entire manifold. All right. So why do I care about this set? Because later on we're going to see that if you assume hyperbolicity, this is what's going to be playing the role of the critical points, right? I mean, if you have an anti-gradient flow of a Morse function, the chain recurrent set is a set of critical points. Okay. I have to go faster to finish this revision. Any questions, please? Please ask me. So, picture to keep in mind of the Morse index is this one. Picture to keep in mind of the chain recurrent set for an anti-gradient flow is a set of critical points. Yes? No. I mean, if you want to prove a theorem, sometimes it's more comfortable to work with. Sure. Okay. So the nice statement now is what's called Conley's fundamental theorem of dynamical systems. Which states that every flow, of course I'm talking about on a closed manifold, smooth flow, but of course it's much more general than that. Every flow is an extension of a strongly gradient flow by a recurrent flow. So in other words, there exists Lyapunov functions. So that's going to be playing the role of our Morse function. Okay? So let me tell you what's Lyapunov function. So Lyapunov function is a function from the phase space such that, one, if you have a point not in the chain recurrent set, then the function decreases strictly. So strictly decreasing. And two, if you have a value taken on the chain recurrent set, then V minus 1 of C intersected with the chain recurrent set is a component of the chain recurrent set, chain component or component. Okay, so in the case of a Morse function, the chain recurrent sets are critical points, right? And everywhere else, the function is constant on components of the chain recurrent set, and otherwise it decreases strictly along trajectories. So this opens the possibility of having Morse inequalities and doing some Morse theory for flows. As I said, if you want to study conservative flows naively, it's not very interesting, right? The chain recurrent set is everything. The function has to be constant. You don't have anything to say. So now it's nice to consider hyperbolicity. Right? So if I have an invariant closed set, so hyperbolic structure is going to be a splitting of the tangent bundle on these invariant sets. Is going to be the flow direction plus an unstable direction plus a stable direction. And then you have constants C lambda such that, well, first of all, these guys are invariant by the linearized flow. And you find constants such that you have a uniform contraction in the stable direction. And you have, for T positive, and you have uniform expansion in the unstable direction. Example, critical point of Morse function. Again, right? So in this case, you don't have this direction. You have, right, the unstable, it says one, just splitting of one vector space, the tangent space there. You have expansion on the tangent space of the unstable manifold and contraction on the tangent space of the stable manifold. So that's also nice. So with this Morse theory picture in mind, it's nice to consider hyperbolicity. I mean, for me, that's the nice motivation to consider hyperbolicity. I mean, very nice, of course. So then you call the rank of the unstable bundle the index of the invariant set. You call this set basic set if lambda, if it's isolated and has dense orbit. It's nice to be isolated if you want to do Morse theory. Actually, as in Morse theory, you can, if you consider the filtration given by the values of the Epilogue function, you have a very nice filtration, which is going to give you very nice isolating neighborhoods for the components of a chain recurrent set.
Isolated means what?
Isolated as in the first line of the talk, in the sense of dynamical systems. Yeah. Okay. So then you have Ismail's spectral decomposition, which says that if the chain recurrent set has hyperbolic structure, then you have that the chain recurrent set is a union of basic sets. So now it's very good, a very, very clear picture comparing with Morse field. You have a finite set of...
It actually holds for any hyperbolic set.
That's right. Right. So you have this, if the chain recurrent set has a hyperbolic structure, you have very nice picture to compare with in Morse field. Okay. So now, what about the local homology? Of course, the local homology, now things become harder. Oh, this is very nice, but if you don't compute local homology, how are you going to get anything? Like, how are you going to get applications out of Morse inequalities? What I mean local homology is the homology of these, the homology of the Conley index of these components. So then you have this great theorem by Bowen and Franks, which was proved in 77, which tells you that if, let's say, lambda I, so I'm assuming hyperbolicity of the chain recurrent set. If this guy is one-dimensional, so this is a precise notion of being one-dimensional, then the homology, the local homology, that is, the homology of the Conley index of this guy is equal to, well, has dimension equal to, let's say, coefficients in a field, so it's f to the ri. If this is equal to the index, or index plus 1. I'll tell you, so Ri, well, this Ri is a non-negative integer, and 0 otherwise. So this Ri is related to, if you have a basic set, if it's one-dimensional, there's a theorem of Bowen saying that you have like symbolic dynamics underlying the dynamics restricted to this basic piece. So this number is related to symbolic dynamics on lambda I, which is, but the good thing about this number is that it's positive.
What one-dimensional means in this case?
Like if you make a transversal cut, it's going to be zero-dimensional. Zero-dimensional means that you can write it as a union of open-closed sets with small diameter. Union of finite number of open-closed sets with small diameter. Like
so suppose that, for instance, take another flow. So the whole manifold is a hyperbolic set.
So that definitely doesn't fall into this.
Yes.
Yeah, so it's very nice, for example, if you look at this isolated hyperbolic orbit, which should be two generators, one in 1 degree up higher than the other.
Where are these circles in the system?
Which circles?
Looks like arc kind of circles.
If you have a hyperbolic orbit, let's say the unstable direction has dimension, I don't know, 30. There is generating degree 30 and one generating degree 31. Which you take this hyperbolic flow near this isolated periodic orbit, let's say, and then you can homotope it to a product flow and then Morsify the S1 part. Have this very nice Morse theoretical picture. Okay. So this is good because then you can compute local homology, at least in this one-dimensional case, you can do some computation. So I'll end my revision just saying that the whole theory works inside a block. Which means that if you look at an isolating neighborhood, let's say inside an isolating neighborhood, if you look at an isolating neighborhood, you can consider the chain recurrent set of the isolating neighborhood. You can consider Lyapunov functions on the isolating neighborhood. You have Ismail spectral decomposition on the isolating neighborhood. So you can do Morse theory, Conley theory in the isolating neighborhood, which is, of course, good because through the isolating neighborhood, you don't have recurrence. So that actually you do have a non-trivial, strong gradient part of the flow inside the isolating neighborhood. So that's the tool. Okay. So this is very nice theory developed by throughout the 20th century, and I'd like to present some applications. So it's a very abstract theory. Being very abstract applies to very general objects, which means it's hard to find applications. If you don't say something about too many things, you don't say much. But so I'd like to present one application coming from celestial mechanics. Which is the following. So the following picture is everywhere present in celestial mechanics. You have a Hamiltonian, let's say in R4, and then let's say it's real analytic. Real analytic Hamiltonian. And let's say you have a critical point. And the Morse index of this critical point is equal to 1. And let's say in that critical level, you only have that critical point. All right. Okay. So let's say the critical value is C, and then let's look at what happens. Let's suppose that at level C minus epsilon, you have some connected component of the energy level, which is diffeomorphic to S3. And perhaps you have other components, maybe non-compact ones, right? And then at the critical level, you have a picture looking like that, the critical point there. And then as you pass critical level, you have these connected sum picture, right? So if you look at level C plus epsilon, you have connected sum picture. So in this neck region, you have the so-called belt sphere. So where is this coming from? It's coming from this very specific belt sphere. It's coming from Moser's. It comes from this extremely non-trivial theorem about normal forms done by Moser, which tells us that you have this belt sphere. This belt sphere carries on the equator this hyperbolic, this orientation preserving hyperbolic orbit, which explains the role of the Lyapunov orbit from the three-body problem. And the flow enters its hyperbolic orbit. The flow enters through a hemisphere and exits through the other hemisphere. Let me draw a picture of the phase portrait. So this belt sphere is looking like that, at least locally. I'm going to cut the belt sphere in the middle. So my picture is going to be a picture of revolution. My hyperbolic Lyapunov orbit is here in the equator, right, coming in and out of the blackboard. I have the stable and unstable manifolds. let's say the flow enters through the southern hemisphere. And exits through the northern hemisphere. And that's the situation. And what's inside here, the topology, is the topology of a tree ball. This side here is the side coming from this side of the picture. This was an S3, and now here I have a tree ball. Is the picture clear? Tell me if the picture is not clear, because otherwise I cannot make any argument. Because argument is going to be on the picture. Okay. So if you have such a picture, and such a picture, well, in this case appears naturally in this huge class of systems, but in many, many other cases, you can actually construct such a picture by using holomorphic curves and finite energy foliations. But if you have such a picture, have a very nice isolating block, looking like, in the sense of Conley, looking like the following. So here, the flow here, so this orbit is hyperbolic. Let's take advantage of the form of the flow near the hyperbolic orbit. So the flow here does that. And then you can continue this box. Like so. Right? So the flow is still entering here. It's still exiting here. Is the picture clear? So what's the topology of, what's the exit set? The exit set is, so this is a very nice isolated neighborhood. If you look at the form of the flow at the boundary of this orange region, the maximal invariant set is contained in the interior. It's an isolating neighborhood. And the exit set is the upper lead. Okay, so the picture is the isolating neighborhood is looking like that. So the flow is tangent to this wall, enters here, exit here. It's tangent to the wall, maybe it spirals, but goes up. And inside here, you have non-trivial maximal invariant set. Right, so if you just look at what happens in the boundary of this region, maybe the flow could be, leaving nothing invariant. Maybe the flow goes through this region as the way I defined in the beginning of the lecture. But in this case, it doesn't, because you have a non-empty maximal invariant set. Which is, you have an invariant set here, given by the hyperbolic orbit. What's the homology? So here's the exit set. What's the homology of the Conley index? The good thing about the Conley index is that to compute it, all you have to do is to look at what happens in the boundary. So in this case, so the homology of this thing modulo the upper lead is equal to 0. So 0. So 0 homology. However, 0 homology, however, non-trivial chain complex. This is something that Hofer has been advertising all the time. It's always interesting to look at situations where you have 0 homology but non-zero chain complex. This is a situation like that. And this is exactly what we can use to prove that inside this block there can be no uniform hyperbolicity. So that's a statement. That's like the model statement about the kind of applications I was intending to talk about, at least in the beginning of the lecture. So let's say theorem. This is joint with Salomon. And also some discussions with Marangidea, which we are trying to generalize this kind of statement. So let's call this isolating neighborhood N. The chain recurrence setting N does not have hyperbolic structure. And this is sort of related to why the Poincaré conjecture could not be proved by Ismail. You cannot remove some connections. And the reason is the following. Right? So you have a Lyapunov function. So let's suppose by contradiction that the chain recurrent set here is hyperbolic. So you have this Lyapunov function. You can filter the chain recurrent set. So here's a component, a basic set of the chain recurrent set, a basic set, and so on. Basic set. Let's see, lambda 1, lambda n minus 1, lambda n. Here I have sublevels of etc. Sublevels of the Lyapunov function at these regular values, let's say. And then, okay, so the key observation, or not key, I mean the trivial observation is that this is a Hamiltonian flow. So if it has hyperbolic structure, each of these basic sets has to have index 1, right? If the index was, direction of the unstable bundle was 0 or 2, you would contradict the volume preservation. So looking at this theorem, the local homologies of every basic piece has to be non-trivial at degrees 1 and 2. And so this means that the chains in degree 1 coming from this top local homology cannot be canceled, contradicting the homology being 0. More precisely, but there is a catch. So this theorem doesn't apply. I will explain. But let's say all these guys were one-dimensional. You could look at the triple M0, Mn minus 1, and Mn. And well, we have a long exact sequence. Let's say H1, M1, M1, Mn, M0, H1, Mn, Mn minus 1, H0, Mn minus 1, M0. This is 0 by this is 0 by recurrence. I mean, if you take a flow here, take a point here, let's say, anywhere, you perturb a little bit to get out of the chain recurrent set, it's going to go down. You have to come back. So it's going to go down to M0. So this is 0 homology. This is non-zero. Oh, let's say this is non-zero by this theorem, which you cannot apply. So this means that this has to be non-zero. This is a contradiction, right? The homology, this homology is exactly equal to the homology of the Conley index. So there is a technical issue here. This cannot be applied because you don't know if this set is one dimension, but still you can prove doing some work, not too hard, but also not too easy, that this is a non-zero group. Okay, so this means that, I don't know if you heard about the Poincaré and the prize of King Oscar when Poincaré basically discovered chaos because of this hyperbolic orbit is essentially forcing chaos to hold, let's say, near one of the primaries of the three-body problem, restricted, planar, circular, below certain critical value. On the other hand, this homological argument tells us that, although you have some hyperbolicity, you cannot have everywhere hyperbolicity. And this is a very baby statement that can be generalized. Actually, all you need to know is, the statement is that if you have a block, let's say you have a Hebb flow, or let's say you have a odd-dimensional energy level, well, you have, of course, odd-dimensional, but you have an energy level of a Hamiltonian system. If you find a block, the local homology is 0, you cannot have hyperbolicity by doing more theoretical arguments like that. But then you have to work a bit, or not so little, but not too hard also to replace this theorem by proper statement. Okay. That was one of the things I wanted to tell you. And the good thing about this is that it has lots and lots of applications. Concrete examples also. Not produced artificially, but actually appearing in mechanics. Okay. So let me tell you another kind of, I have until 5:30? Okay. Let me tell you about another kind of application of this reasoning, which is related to global surfaces of section. Of course, I mean, this example in celestial mechanics is, I mean, let's say in the three-body problem, everybody knows there is no hyperbolicity. Because you look at the computer, you have elliptic islands showing up everywhere, and so on, so on, so forth. But this is a proof in more general situations, even higher dimensions. I should also say that it's possible to obstruct not only uniform hyperbolicity, but it's also possible to obstruct much weaker versions of hyperbolicity. But I can discuss that later. Someone wants to know more about it. Okay. So the notion of global surface of section has also appeared many times during the workshop. So what is it? It's a surface whose boundaries contain some link of periodic orbits of a three-dimensional flow, and every trajectory, which is not in one of these periodic orbits, will hit this surface transversely infinitely many often in the future and in the past. Which is also very nice because then you reduce the dynamics to this return map, which is a two-dimensional object, so we have much more tools and so on. Okay. So let me tell you a bit of what can be proved in general, not even for Hebb flows, but even more general. So if you have a three-manifold and a link of periodic orbits, and let's say you have a homology class in degree 2 model the link. The question is, does this link bound the global surface section in this homology class? And for the discussion now, I don't assume that the global surface section is a cipher surface for this link. It could be multiply over in the boundary. Okay, so you have a rotation number, which is I'm going to explain, given by this formula. So what is this formula? So I'm looking at the periodic orbit gamma I. Ti is the period. I have a neighborhood which is looking like circle cross disk, and with coordinates t. So this is a tubular neighborhood of gamma I. Here I have coordinates t and theta, angular coordinates. So I take the dual, the one homology class, the degree 1 cohomology class in the complement of L, which counts intersections with this homology class. Here I take z coefficients, here maybe real coefficients. And then I can write this guy as P dt divided by Ti, at least there, right, on the neighborhood. It's homologous to this one form. So then I have a rotation number where this theta I is really the transverse linearized dynamics, the angular linearized dynamics along the orbit. It's a rotation number. Okay. I also consider the set of Borel, set P phi of Borel probability measures, which are phi invariant. Borel probability measures in the complement. Okay? And then I can consider the linking number with this measure with the class F, which is this integral BF at the vector field where what is BF? BF is a suitable representative of YF. Right? So you take my dual form represented by a suitable one form. I evaluate the vector field, get a function integrating the complement with respect to this Borel probability measure, which is invariant. That's a linking number, some sort of linking number between the cohomology class, the homology class F, and this invariant measure. So the way to think about it is that the invariant measure is like some sort of generalization of the notional periodic orbit. Right? So I have this linking number. Right, so if this was counting intersections with, let's say, a cipher surface, this would be exactly, this form would be like a bump function in the normal direction of the cipher surface. You count one every time you cross. Okay, so the theorem essentially according to G, is essentially due to Schwarzman, Fried, Sullivan, is the following. If the rotation number at all these periodic orbits is positive, and the linking number with all invariant measures is also positive, then L spans a global surface of section in class F. So we have this global surface of section representing the class F. Actually, the converse is also true. You just need a little bit of non-degeneracy, but today I don't want to discuss the converse. But the converse is also essentially true. So there is, every time someone finds a global surface of section, one is checking the hypothesis of this theorem. I'll talk a bit in a few moments. In the class of Hebb flows, you can considerably make this statement stronger, but I'll come back to that in a second. Okay. Are there any questions about this statement? All right, so let's say we have a flow. Let's say it's even a Hebb flow. Well, it doesn't matter too much. Have a flow. And our link of periodic orbits is given by a fibered link of periodic orbits. What does it mean? It means that L is the binding of an open book decomposition. That's what it means to be fibered. And let's consider a page. So this is just a leaf on this vibration in the complement. Are there any questions about fibered links? Okay. So I'll say that sigma is strongly transverse to the flow if the rotation number of the class sigma on all gamma I is positive. Right? So I have this infinitesimal transversality at the binding orbits, and also that the flow is transverse to the interior of the surface. So it's like a strong transversality. So here, in the interior is just the usual notion of transversality. In the boundary, you need this positive rotation with respect to the cipher surface. Okay. So let me consider so what's the key observation? Key observation. The complement of this strongly transverse surface is an isolating neighborhood, essentially. Let me put it that way. The maximal invariant set of the complement is contained in the complement. That comes from the transversality here, and also this infinitesimal transversality here. So this puts us in business to use Conley theory to say something. Okay? Then, let's say, corollary of the previous discussion. Well, previous discussion was an example, but this is another example of the same theorem, which I will probably not state. If you have something invariant in the complement, which means that this very nice surface, which is very nicely transverse to the flow, wants very much to be a global surface of section, but it's not. That's this assumption here. Then the chain recurrent set in the complement does not admit hyperbolic structure. Here I'm assuming Hep flow, right? So it's an interesting phenomenon that's happening all the time. You know, it's a fibered link. For sure, the Conley index is 0 because there is. You can modify this vector field outside of the surface in such a way that this will be a global surface section for this other flow. And that's the power of Conley theory. You have the continuation argument, which tells you that the homology doesn't change. So the homology is 0. By the same arguments as before. However, if the chain complex is not 0 for the homology of the Conley index, then you can prevent hyperbolicity again. So this is the same phenomenon again and again. So now, in the last 5 minutes, I'll just like to discuss a bit more about global surface section. But before, how is this more general theory of global surface section related to this statement? So I would like to make a conjecture, but I don't think maybe it's too early to make a conjecture. Maybe more like a question. So the question is there a local Weinstein conjecture for a Hep flow? So the question is, given a Hep flow on a 3-manifold, and suppose you have S, a non-empty, isolated, invariant set. Maybe assuming that the homology of the Conley index is different than 0, maybe not. So the question is, does this invariant set will carry a periodic orbit? be very nice if this conjecture could be shut down in 5 minutes, but I don't know. So why is it related to what I was telling you before? So theorem with Salomon and Vysotsky states that, let's say L. So now I'm in the context of Hebb flows. Let's say I have a link consists of periodic orbits, but I will say that, so this 3D Hebb flow, I have L planar fibered link of periodic orbits. Sigma, a strongly transverse page. So here, Gino 0, because I'm taking the open book of Gino 0 pages. So suppose you have this, then if in the complement if there are no periodic orbits in the complement, then L bounds Gino 0 global surface section. Actually, that's a special case of a more general theorem, but and the converse is also true, but I just like to point out the following corollary. This local Weinstein conjecture holds for this kind of isolated sets, for the isolated sets you get in the complement of these strongly transverse surfaces. So local Weinstein conjecture holds in the complement of a Gino 0 strongly transverse page. In the context of the other kind of isolating blocks I was talking about before, this local Weinstein conjecture was proved by Eliash, Berman, and Hofer. Okay, so I'll stop here. Thank you.
Questions?
Yeah, this